Good morning or good afternoon, depending on where you're located. We're very excited today to have a demonstration of the Drought Data Dashboard. My name is Britt Parker. I'm a Senior Program Manager with the National Integrated Drought Information System, and we're happy you all could join us here today. I just want to give a brief introduction about NIDIS and the effort that led to this dashboard, and then we will launch into Zach's presentation. So we're joined today by Zach Hoylman with the University of Montana and the Montana Climate Office. He's the Assistant State Climatologist, and he'll be doing the demonstration this morning. So the National Integrated Drought Information System is a multi-agency partnership that coordinates drought monitoring, forecasting, planning, and information at federal, tribal, state, and local levels across the country. We do this work through regional drought early warning systems. We also support drought planning and preparedness, impact assessment, and really work to strengthen collaboration and networks of partners across these regions, as well as the nation. And everything that we do, as well as collated drought information from across the federal agencies that provide drought information, can all be located on the U.S. Drought portal at drought.gov. So our primary goal is really to enable the nation to move from a reactive to a more proactive approach to managing drought risk and impact. I want to flag that this is our 20th anniversary, and so there's going to be multiple opportunities this year for you to learn more about NIDIS and our partnerships. We are going to complete the build out of our national drought early warning systems across the United States. We are looking forward to celebrating our interagency and intergovernmental drought partnerships through events, communication efforts, case studies, and videos, and really deliver a vision for the future of NIDIS that broadens the network of partners to expand our nation's early warning capabilities. And as you'll see, as this is an excellent example, our interagency, cross-sector collaborations and partnerships are key to everything that we do. So this effort really started with our Missouri River Basin Drought Early Warning System, which was launched in 2014. In 2017, the Northern Great Plains and the Canadian prairies were hit by a flash drought. And we came together across the states of the region and our partners in Canada to assess the impacts of that drought, as well as the causes and predictability of that drought. And part of what came out of this effort was the need to better coordinate across the region, the need for better access to drought indicators and information for assessment. And from that, this concept of a drought dashboard in the Northern Great Plains was born. In 2020, 2021, the region was hit with another drought that was quite impactful. And one of the things that came out of that second drought was that communication had improved and access to information was continuing to improve, and that allowed us to assess drought conditions and react more quickly. We've also worked with our tribal partners across this region to engage them in drought assessment and drought preparedness. From a lot of these efforts, a first iteration of the dashboard was launched and made available. And we started exploring the impacts of non-stationarity of the climate system on how we assess drought. And that led to a number of publications and a technical memo on drought assessment in a changing climate, which then led to a very recently released National Academy study on how to improve the future of drought assessment in the United States. And I'll let Zach talk a little bit more about how some of these things are related, but I just want to stress that it's been through strong partnerships across the Northern Great Plains that this dashboard and what you'll see today have been developed. Just very quickly, for questions today, you'll be using Slido. In the browser, you can click the Apps button and type your question and send it, and I'll be moderating the Q&A at the end of Zach's presentation and demonstration. If you're in the WebEx app, then you can just click the Slido button and type your questions and hit send. So please feel free to put your questions in the chat at any time. And with that, I will turn it over to Zach and let him start his demonstration.
Got to unmute myself there. All right. I'm assuming everyone can hear me. Thank you so
Yes.
much for the introduction, Britt. And I'm really excited to be here today to talk about our new drought data delivery system that we're calling D3, or the Drought Data Dashboard. And as Britt was saying, I want to start this presentation by really emphasizing that this work is, and this dashboard is really the culmination of over a decade of work in the upper Missouri River Basin, across Montana. And it really represents a long collaboration and co-production process with partners across sectors and across scales. So this work, the D3 dashboard, really has been supported by state entities like Montana Department of Natural Resources and Conservation, from NIDIS, the National Integrated Drought Information System. It's been supported through funding through NIDIS, and also more recently through an NSF project, which was part of the R2I2 call, which is part of this NGP rider, or the Northern Great Plains Regional Incubator for Drought Resiliency. And so, while I'm presenting this work and presenting this dashboard, please know that this work really represents a really, really collaborative effort across many, many, many partners. And so before I start, I just want to say thank you to everyone who has contributed meaningful feedback, helped me to refine this dashboard, and really created a system for drought data delivery that is useful across different scales. So with that, I'm going to go ahead and get started. When we're talking about drought dashboards and we're talking about drought data, we're going to spend a lot of time looking at maps, and I might even say the word probability distribution once or twice. But I think it's really important to contextualize this work with why we even do drought monitoring in the first place. And I think most of the people in this room know that drought monitoring informs billions of dollars in decisions every year. And those decisions and that money is really distributed across many, many, many sectors across our country. Of course, drought impacts things like agriculture and ranching quite dramatically. In Montana, where I do a lot of my own work, we think about dryland agriculture, we think about rangeland production and livestock production, and drought is just so impactful to those sectors. So drought monitoring is really important for understanding the potential impacts that might be occurring to those sectors. We know that drought obviously has strong impacts to water supply and reservoir operations, and this really scales to, massive systems like the Colorado, to, small irrigation districts in, northeastern Montana, where, there's much more kind of local representations of these reservoir operations. The other thing about drought that I think a lot of people recognize is that it's a cascading hazard, and that a lot of the time drought can be a trigger or can exacerbate conditions that create other catastrophes or amplify other catastrophes like wildfire. So drought's really key for that. But if I look at this bottom right-hand photo, this is from Hill County in Montana earlier in April. And what I think of most, and the most impact that drought assessment has and drought monitoring has, from my perspective, is really emergency management and disaster response. And when I see landscapes like this from Hill County, Montana, I often think about the data that might represent these conditions, but I really think about the communities that are being impacted by drought. And that is really what drives my kind of my motivation to create new systems and more accurate drought monitoring capabilities across the country, because at the end of the day, we really want to represent these conditions well. And anyone that knows me, it will also know that I am a bit of a fly fishing nut. I spend a lot of the time on the river, and drought has really important impacts to ecosystem dynamics and natural resource management. So not only does drought kind of scratch my academic itches and really, I think, have a lot of impact to society, it also really impacts me personally in my recreation. And that's why it's such a meaningful kind of component of my academic adventure so far. And at the end of the day, I hope to argue that better drought information leads to better decisions. And that's really the key to this dashboard, and the key to the work behind this dashboard. All of the science is really to produce better information so that we can make better decisions. So you might be thinking to yourself, okay, there's, lots of data delivery systems out there. Like, why does drought monitoring, in quotes, need to evolve? And I think that there's a good argument for this around three major developments that I would argue are really reshaping drought monitoring right now. The first is, of course, that climate is changing. So what I'm showing you here is a map of temperature trends across the country. This is from NOAA's NCEI, and anywhere on here shows where there's a significant trend in temperatures since 1895, so over the last 130 years or so, 135 years. And what you can see is that across the country, we're seeing kind of dramatic trends towards warming conditions. And warming conditions don't just mean a hotter atmosphere and a hotter environment. They have huge cascading impacts to the hydrological systems that really drive drought. As temperatures rise, we have more atmospheric demand, or the atmosphere has a greater capability to absorb water, and it's a thirstier environment is the way that we kind of describe it. Right. And in response to this change in the hydroclimatic state, the science of drought has been advancing as well. And recently, there's been strong recognition that these changes in hydrology and hydroclimate have significant impact on our perceptions of drought and how we define drought. And that really is because a lot of the models that we use to describe drought are based off of what we call probability models or probability distributions. And one of the core kind of assumptions, inherent assumptions of these distributions, is that the data that you use to conceptualize or contextualize current conditions, think of it as like a climate normal, is what we call stationary in time. And these are the traditional drought models that I'm referencing here. So what that means is that we're assuming that the statistics of that hydroclimatic condition, say precipitation or evaporation, is relatively consistent over time. And we can use that probability distribution to describe today. But what we know is that as the climate is changing, so too are the statistics of drought. And therefore, we have non-stationary systems, non-stationary drought systems, which impact our perceptions of drought. And so when we make an assumption that the climate, say, of the early 70s or early 80s is roughly similar to current contemporary climates, we really change our drought perceptions. And it turns out we might actually overemphasize how significant drought events are with respect to that contemporary climate. And that's not to downplay impacts. The point here is to be very accurate and to be as accurate as possible about current contemporary drought risk when we're describing current conditions so that producers and ranchers can make the informed decisions they need given current contemporary conditions. And the final thing is that technology now exists to make modern drought assessment really operational and really, really nice. And so at the intersection of these is where D3 is meant to build. So we're really trying to build this new dashboard to acknowledge these changes and these developments in drought monitoring and leverage these new systems that we have, including cloud computing infrastructures, modern dashboard development, to create a system that really provides good drought information in a modern way. And I've been saying modern a lot. And when I talk about modern drought assessment, I really think of it in the context of modern science. If we think about science over the last 50 years, things have changed quite a bit. And what we expect as scientists in terms of things like transferability and reproducibility and data availability have fundamentally changed. And so we're lucky to have this new kind of report that came out of the National Academy of Sciences help us to think about what a modern drought assessment system looks like and what we should strive for. And the first thing that I think modern drought monitoring really requires is transparency and reproducibility. And that goes across scales. That goes into methods, data, and uncertainty. The second is flexibility. we know that drought is a very multi-disciplinary system and phenomenon. It is responsive to many different things. And so when we're defining drought means different things to different systems and different people. And so we need flexibility in how drought is assessed and defined in many different ways. And we'll kind of dive into that in a minute. We need integration of many different data sets and many sources of evidence. And this goes across gridded information to point information. And we need really useful ways to integrate all of that, right? We need a strong emphasis on co-production. This is something that I've learned following graduating from my PhD, that the importance of co-production is paramount. We need our systems to be iteratively developed with decision makers and partners to ensure that they meet the needs of these people that are using these systems. And finally, we need to embrace innovation. There's huge innovations occurring in the realm of emerging observations at local scales, like state level mesonets or regional level mesonets, along with these next generation models like machine learning models for better predictions of different variables. So all of these are kind of components of a modern drought monitoring system. And D3 is really trying to put these principles into practice. So it's designed around these 5 guiding principles. And I'll kind of say how, and then we'll dive into each one. And what I'm showing you here on the right is a screenshot of the dashboard. And don't worry, we're going to spend a lot of time kind of getting used to it and looking around at its capabilities. And I'll even do a live demo. But before that, transparency is really at the forefront of the development of this dashboard. And that comes in the form of open methods, open code, validated and reproducible products, and many other things. And so I'll show you later on how you can scrutinize the decisions that go into these dashboards and how things are calculated. Flexibility, that means many different things. That means multiple reference periods. It means trying to create a system that supports many different decision-specific workflows. And we have a new tool that allows you to create custom objective blends. It's in what we call our convergence of evidence tool. And if you're familiar with the great work of NDMC, the National Drought Mitigation Center, and their objective blends, this is kind of a user-defined version of that kind of concept. And we need integration of multiple indicators, observations from different scales, national to local, gridded and station data. So we need a flexible system for integration. Again, co-production is key, and innovation. So I'm going to tell you a little bit about the machine learning products and next generation, in quotes, drought information that we're producing in this dashboard. So let's go ahead and just kind of get oriented a little bit and think about D3 at a glance. So this is the dashboard, and what you can see is we have kind of a control panel on the left and then a data visualization thing on the right. And what we first start with is kind of our core base of the dashboard. And this is what we consider kind of the Analyze tab or the Analyze area. And it's really a fundamental and core part of the dashboard. It allows you access to 20 plus drought indicators. It allows you to do analysis at different timescales, 11 different timescales. We'll talk about what that looks like. But of course, drought isn't just the amount of precipitation that's occurred over 30 days. It's important to consider 60 days, 90 days, a whole year of data when we're talking about different impacts, different cascading impacts of drought to different systems. And then importantly, we have 3 different reference periods that you can choose from. And this allows us to really explore the impact of non-stationarity on drought definitions and drought severity kind of perspectives. Next, we have kind of tools for integration. So I think of this as, integrating station data. So bringing in things like GHCN data or the Global Historical Climate Network data set to compare basically point observations to gridded observations with the idea that they really represent different things and different scales. And so I'll talk about that in a moment as well. And then we have quite a bit of opportunity to share, and share information goes many ways. It goes in the form of exporting maps and being able to produce nice screenshots with good data attribution, or having resources to understand the underlying information, or report drought impacts through the National CMOR program, or provide feedback to me and our team at the Climate Office to make improvements or support new feature requests and share information. And so that share goes both ways. It allows us to share information about drought analysis and drought insight that we may have gleaned from this dashboard and other tools, but it also allows for people that are being impacted by drought to share that information back to the drought science community doing assessments to really balance those two different needs and perspectives. So before I go into the live demo, I kind of want to highlight 4 main capabilities in this dashboard that I think really provide a lens of its kind of novelty right now. The first is flexible reference periods. I'll show you kind of the impact of that with an example. Again, the convergence of evidence approach in our new tool, integration of data across scales, be it raster data or point data, and some just kind of highlight a few of the machine learning products that we're producing that are in prep and in review currently. So let's start with non-stationarity. And again, this is to describe kind of how the statistics of drought are changing over time. And so what I'm showing you here is 2 different maps. They're both the standardized precipitation evapotranspiration index calculated over a 90-day period. And what we're changing here is the reference period, or the period of time that we use to define what our expected conditions are, or you can think of it kind of like a normal. On the left is the most recent 30 years. So this is 1997 through 2026. And on the right is the full period of record, which is roughly 48 years. So it's 1979 to 2026. And again, like I said, the core kind of assumption at the base of these probability statistics that we use to make these models is that the reference periods that we use to describe current conditions are stationary over time. And therefore, what happened in 1979 is a good statistical approximation of what could happen in 2026 in terms of likelihood. And so what you can see is when we use really long periods of record here in this example, we see a lot more dark red on that map, showing that, given a 50-year period of reference, we would expect that these conditions occur maybe once every 50 years, once every 100 years. But as we're transitioning and the climate is warming and atmospheric demand, which impacts evapotranspiration, is changing, that those conditions are actually more likely in the more contemporary climate. And so what that means is that if we reflect that information, that this is actually occurring more commonly than it was in the past, that is hopefully will help people to have greater preparedness and understand their current contemporary climate risk as they move forward and make decisions about what their operation might look like in the next year or in the next 5 years. The next is this convergence of evidence tool. And this is something I'm really excited about. If you've ever done drought assessment, basically what we're tasked with doing is taking lots of different information, lots of maps, and trying to understand where they all kind of align in terms of the severity of drought. And that could be a really challenging thing to do, just toggling between maps. And so this tool is really meant to help with that process. And what I'm showing you here is the median value of 44 different drought maps computed on the fly based on a user's decisions on what they want to include. So this is the standardized precipitation index, the standardized precipitation evapotranspiration index, the evaporative demand drought index, and the standardized vapor pressure deficit index. And I've calculated that over many timescales: 15, 30, 45, 60, 90, 120, 180, 1 year, 2 year, water year, and year to date timescales. And then what we do is we calculate the median value across all 44 of those maps on the fly within the browser at each pixel level to give you an idea of where all of these maps might align in terms of their reflections of drought. And there's a bit of like a nuance here that for the probability statistic nerds out there like myself, this should not be confused with a joint probability distribution. This is simply taking all 44 of those maps and calculating the median value across them all, which there is kind of some important differences there. But I thought I'd just throw that out as a quick caveat. But this is a really cool tool that I think allows for that reproducibility and transparency in how you're defining drought, and really provides an analytical way to quantify that convergence of evidence. The next thing is integration. So when we talk about drought assessment, we're often using many different data sets, gridded and point. And so what we're seeing here is basically utilizing both gridded information of drought conditions along with point observations. So this shows on the left raw precipitation accumulations from GridMet and the GHCN data set. These are updated daily and allow you to basically see how the point data might reflect current conditions versus the gridded data, with the understanding that these different data sets fundamentally represent very different scales of observations. Gridded observations like GridMet are meant to represent conditions across an entire 4-kilometer pixel, whereas a point observation represents a hyperlocal condition or observation. And that obviously makes huge differences. In Montana, we have convective systems that come through during the summertime and might create a storm track that's only a few miles wide. And that might be much better represented by point observations versus gridded data that's trying to represent kind of those average conditions across that 4-kilometer pixel. So this is a really nice way to kind of think about complementary information at different scales. But what about local information? That was at the national scale. We've also produced a system, a flexible local plugin support system that allows you to contextually activate different data sets. And what I mean by that is that you can zoom into Montana, and when you have Montana kind of taking up a large portion of your screen, you can access information from the Montana Mesonet. So what I'm showing you here is you click on a point and you're able to see time series of soil moisture from the Montana Mesonet, which is very, very important for our drought assessment process in Montana. And you can imagine how different states might have different networks that they want to include in this dashboard. And we're creating this flexible tool that allows for that activation of information. That'll, of course, require collaboration between our office and your data sets and your dashboards. But this is something that we really strive to integrate into this dashboard. And what's really key about this is it allows for us to make very clear attribution about where data is coming from. So you can see down here that we have the Montana Mesonet logo pops up. And as we all know, I think attribution is absolutely paramount for creating durable products. If we're not doing a good job about making attribution, then it's not understood what data sets are so fundamentally important for these drought assessment tools, and it makes us aware of the support that's needed for these tools to persist. So finally, before I dive into the dashboard and the live demo, I just want to show you some of the kind of emerging products. These are, again, kind of more, they're coming out as we speak. And these are knowledge-guided machine learning products that we're producing in the Montana Climate Office. The first one is for streamflow and engaged basins. So this provides daily simulations at the Huck 10 scale. We also have a Huck 12 scale data set as well that allows you to look to see how conditions, streamflow conditions, are estimated to be evolving across all of the basins in the country, whether there's a gauge there or not. So that's a really useful thing. And then we're also using knowledge-guided machine learning to basically leverage process-based models, like in this case, the Sport LIS model, to basically leverage those process models with data-driven observational approaches to make the most accurate soil moisture models possible. And we think that in the future, modern drought assessment might leverage these quite a bit as better representations of state variables like soil moisture or stream flow, and might provide us a way to be a little bit less reliant on meteorological proxies of conditions versus the things we really care about, like stream flow or soil moisture. If you're a nerd like me, it's always nice to understand kind of how things are going on in the background. Another component of a modern system here is that we have a modern drought kind of calculation system going on. So all of the analysis is being done nightly in AWS through what's called an ECS, or an Elastic Container Service. And this is a way for us to basically deploy Docker containers, which are basically virtual machines, virtual computers that we can spin up and destroy, and we can put them into the cloud and allow them to run really efficiently to produce the information nightly and do that in a decentralized way. So you can imagine if at the University of Montana, the power goes out or internet goes out, if we were serving the data from the university, that would mean that that information is no longer available on the dashboard. But through these systems like AWS, we're able to put those off premises and make them more durable. And also leverage resources like Amazon's S3, which allows for really quick I/O of data and allows for large throughputs of information as well. Finally, the transparency and reproducibility is, like I said, paramount to this dashboard. And all of the code that has gone into developing this dashboard, developing the underlying data sets is available on GitHub for your scrutiny. We welcome it. And then we also have human readable methods documentations that allows you to go in and really see how things are calculated, all the way down to the nitty gritty kind of nuanced decisions like, how do you handle zeros? Of course, precipitation is often modeled with a gamma distribution, which doesn't play that well with zeros in some cases. So how do we handle that? All of that is documented here in these methods. And before I show the live demo, I just want to take a step back and say that this dashboard is not possible without national and local data sets and data delivery systems and partnerships across these different scales. So it's just really key for us to recognize that none of this is possible without academic partners producing data sets like GridMet, or the USGS that's collecting these streamflow data sets, or NOAA that is collating all of the GHCN information, or the satellite information coming from NOAA STAR, or the Montana Mesonet, et cetera, is just exceedingly key for these types of systems to persist. And I just want to put a pitch in that this is another reason why it's so important for us to continue to support all of these diverse systems, because as we build new tools based on top of them, maintaining them into the long run is just absolutely essential for us to have a more prepared nation for drought in the future. So with that, I'm going to go ahead and just dive straight into the demo. So we're going to click on here. So now I'm hoping you all can see it. I'm just going to assume you can. This is what the dashboard looks like right when you bring it up for the first time only. Basically, it gives you a little bit of information about kind of orientation, what kind of data is on here, gives you kind of an idea of what export and share capabilities there are. But really important is our partners tab. You can click on that partners tab and see exactly who has been contributing data, get links to their websites to understand kind of where the data is coming from, and some of the partners that have been key to developing this. So again, trying our best to attribute as much of this information that goes into this dashboard as possible. And, if you notice something that's not represented well, please let me know through the feedback button. I'll show you that in a minute, and we can make those changes. Okay, so first, of course, we've got our kind of toolbar on the left that allows you to access all of the different information. And on the right, we have our kind of main data mapping system. And so what I'd start with is, of course, our data layers. So if you click on this tab here, it has a drop down and you can see a bunch of different data sets. We have drought metrics like the standardized precipitation index, the standardized precipitation evapotranspiration index, eddy, vapor pressure deficit. We've got some of our knowledge guided machine learning products. We've got some different raw precipitation data, temperature, vapor pressure deficit, SNODAS-based standardized SWE anomalies. We have some remotely sensed information about vegetation from NOAA STAR. And so if we start, we can just click on something like precipitation percentiles, and you can see right off the bat where we've had, lots of precipitation. We had this big precipitation event over the last couple weeks in Southwest Montana. And of course, down in Colorado, there's some pretty dry conditions. We'll explore that later. You can click on things like temperature percentiles or temperature deviations from normal, for example, to see where things have been warmer or cooler than normal. You can go to vapor pressure deficits. You can go to remotely sensed information like VHI STAR. Like I said, this is the vegetation health index. Blue is healthier and happier information. Vegetation. And you can do some cool things here with this data set in particular. What we do in Montana is go back a year and look at 2025 versus 2026. It can be useful to contextualize a recent event. And so there's just lots and lots of data here, and we'll go ahead and kind of explore that in a minute. The next thing that you can do is change the time scale of your analysis. So what we see here is this is looking at SPEI over the last 30 days, but you can look at it over the last 45, 60, 90, etc. Go on to 1 year, and you'll see that depending on the time scale of assessment, you get very different depictions of drought severity. And that's an important part of drought science and drought analysis, is reconciling these different perspectives based on different time scales and variables, right? So let's say we're interested in Colorado and we zoom into Colorado, and instead of looking at this as like a gridded data set, and of course this is all interpolated slightly, so you can go to the raw data or the interpolated data really quickly to see the raw data. But let's say you want to understand kind of county level average conditions. What you can do is go down to this overlays tab here, go down to county, and you can hit median here, and it'll on the fly calculate the median value for that county of all of the pixels within that county, which is pretty neat. And that, again, is all happening browser side on your computer. You can say switch back and forth so you can see kind of what's driving those conditions. You could go to the state level, which may or may not be useful depending on what your intent is. But we also have other data sets on the overlay like tribal nations. So you can access data directly from BIA and see the different tribal nations and how drought conditions kind of are reflected with respect to those geographic boundaries. You can do the same thing for something like watersheds. So for example, maybe I'm interested in Huckate subbasins across Colorado, and that tells you a little bit about meteorological drought with respect to these subbasins. So that's all really useful. Of course, with drought assessment, we're never starting from scratch. We're always pretty much starting from the previous week. So a key data set, thanks to NDMC, of course, is the US Drought Monitor. And so what we can do is toggle on the US Drought Monitor. And I just want to show you one capability of this dashboard that I find really useful. In Montana, we have a rotating number of authors. And so my week pops up. And the first thing I do is I say, okay, I want to understand kind of how drought has evolved over the last several weeks so that I can see kind of the trajectory of drought. So what I do is I'll go back a couple weeks, say go back to the beginning of June. You can use this slider to go back in time and then click forward in time and see how drought has progressed up to the week of my analysis. So you can do this across big swaths of time, which is really useful for thinking about kind of how drought has been evolving and puts your current assessment into that context, which is useful. Or let's say you want to say how current conditions compared to 2017 drought. Britt was talking about the flash drought that occurred in 2017. So you can go back in time and see how extreme those conditions were back in 2017 and then bring it right back up to current really quickly. And that's something that we've found really useful. You can turn that off over here. And before I get rid of the overlays, I just want to show that there's kind of a quick toggle over here as well that allows you to access those kind of general overlays quickly and easily here as well, like that. Boom. Cool. So now we'll go ahead and close that up. The next thing I want to show you is the impact of reference periods. So if we zoom in Colorado once again, and we're looking at conditions here with respect to 120-day SPEI, what you can see is if we change our reference period from the most recent 30 years to the last 50 years, we see a pretty dramatic difference in how severe those conditions are represented. This is that impact of non-stationarity on drought assessment and really shows how the choice of that reference period really has huge implications for our perception of how severe that particular drought event is. And we can look at this also from the perspective of the convergence of evidence tool, which is pretty cool. So you go down to convergence of evidence here. And let's say I'm doing a drought assessment in Colorado and I want to say, look at the last 60 days of data, the last 90 days of data, the last 120 days of data, and the last 180 days of data. So now we have 60, 90, 120, and 180 day timescales for SPI, SPEI, EDI, and SVPDI. And so what we're going to do is we're going to calculate the median value of all 16 of those maps, right? So what we do is we come down here, hit compute composite, And again, that all happens in the dashboard on your browser. Then you can click on a point and see how all of the different metrics basically represent current conditions, and then see what the median value is across all of those conditions, which is pretty neat. You can also do this across different reference periods. So go to the full period of record and see across that convergence of evidence how much that reference period matters in terms of defining how severe drought conditions are. Now, you might be looking at this and say, hey, streamflow in Colorado is at record lows. And this is, again, this idea that meteorological information is only one piece of the drought assessment puzzle. And we'll look at streamflow in a minute. But before I get there, I want to show you a few more things first. Okay, so station data. Let's say we're looking at precipitation accumulation across Colorado. Here it is. And we want to say, okay, this is GridMet's representation of current conditions, let's say over the last 30 days. How does that compare to the GHCN data? What we can do is we can go to the station data and hit the GHCN toggle, and it'll turn on all of the GHCN points that have the last 30 days of complete data, in this case, right next to the GridMet representation of that data. So you can go ahead and click on a point and see, and then get the accumulation from the station data right next door. So that can be really useful. When you zoom out, of course, the color bar that is associated with Colorado is very different than what is represented at the national scale. So you can go up and hit this auto button to rescale it to better reflect the conditions across the entire country. Or you can zoom into something like Nevada and hit that auto button, and it'll rescale it just for your viewport, which is a really useful tool. This doesn't only occur for raw precipitation. You can add something like the standardized precipitation index and really see how gridded representations compare to these point observations. And you can see in general, they have quite strong alignment. So that's some of the point data that's pretty cool. Okay, now let's say in Montana, we know that we have the Montana Mesonet. If we zoom into Montana like this, now what we can see is that this Montana Mesonet soil moisture tab is now activated. We have a logo down here with a URL to the office's basically webpage for attribution. And you can click on this and see the soil moisture data that's being captured by the Montana Mesonet. So you can click on a point and see the actual time series of soil moisture represented at that point. So this is that kind of contextual activation of local data that we think is really useful and might be a good model for other systems. Okay, getting close to the end here. Let's see just really quickly one of the knowledge-guided machine learning products. This is streamflow. And what this is, in Montana, we're really lucky. We have an incredible wilderness area called the Flathead, the South Fork of the Flathead, the Bob Marshall Wilderness. And these are places that have never had stream gauges in the headwaters. And now we can use these new age knowledge-guided machine learning products to basically simulate streamflow with long periods of record. The last 30 years are represented here to say, what is streamflow doing in the middle of the backcountry where we've never had observations? This is really useful. And what you can do is zoom into somewhere like Colorado, where we're, of course, seeing lots of impacts, and see how current conditions really just are dramatically different than the historical past as simulated by this model. You can turn on other point data sets, for example, USGS data, to then see how the modeled data agrees or disagrees with the observations. Again, with the idea that we're representing data at different scales, and so some discrepancies might make sense in a lot of places. Okay, the last things I want to show you are really aesthetic and sharing. So when we move out to the dashboard, we have a couple of different themes that you can choose from. Base maps, you can go to satellite data, you can, change the transparency to see kind of conditions like a standard GIS platform. Go back and see kind of what you like in terms of a base map, in terms of different themes. Those are kind of fun. And then let's say you wanted to make a nice export. You zoom in on Nebraska and you want to export this map. You can go here and export nice PNGs at different resolutions. You can actually download the GeoTIFF directly from the dashboard, or you can access COG URLs. I'm going to show you now, you can go to different resources. So we've got the methodologies all in human readable format, or you can access the actual GitHub source code for these different tools, right? You can click on here and see how we do everything. That's all publicly available. We have tips and shortcuts that might help you orient and see new features, partners and acknowledgements. Once again, key to this. We have an impact reporting pass through to CMOR, which is National Drought Mitigation Center's kind of impact reporting system. So you can go there and report impacts. You can hit this feedback button to submit a Google form to talk about bugs that you may have found, or feature requests, data questions. This is, again, that co-production and collaborative system. We welcome this type of feedback to make this a better tool. And the last thing I want to show you is the share button. So if you were to go over and do an analysis, say in Illinois, and you wanted to share this map with your colleague, you could come here, hit the copy clipboard button, go to a new tab, and now, boom, hit that button and it'll generate the map that you're looking at directly. And this is really cool. You can even do this with the convergence of evidence tool. Say you want to look at all the 60-day metrics here. You like this blend. Maybe you add a custom weight to it and add this to 0.8, and you compute that composite. And then you go over here, you hit the share button. You can send that exact same map down to the custom weights to your colleague and regenerate it on the fly, which is really useful and might be a good way to kind of share drought information dynamically with your partners. So with that, I'd just like to say, once again, thank you to everyone that has been so paramount in the development of this product, the collaboration that this dashboard represents, and I truly hope that it's a useful tool for drought assessment across the nation. So thank you very much.
Great, thank you, Zach. We do have a few questions. Again, please use the Slido feature in WebEx in the platform to submit your questions. The first question, Zach, is the shift from the rolling 30-year to the period of, period of record is similar to what NOAA has done for the ENSO shift from ONI to RONI for SST trend monitoring for determining El Nino and La Nina. Did you use a similar template for drought?
Yeah, so here we've used a 30-year period of record. That's a rolling 30-year that updates every year. So as we go into 2027, we will incorporate 2027 into that probability distribution and, get rid of the previous year. So I'm not fully familiar with how that rolling ENSO metric is calculated, but I assume they're very similar. You can also just use a climate normal here, a 1991 to 2020 climate normal, if you're interested in kind of using a more traditional WMO style climate normal. But I would have to review the actual methods used by that rolling ENSO metric, but I assume they're quite similar, yes.
Great, thank you. I think you sort of answered this, but I'll let you dig a little deeper. Once you've created a look on the D3, are you able to download the underlying data on a regional basis? For example, download the percent of normal precipitation or SPI for a region, state, county, watershed point, etc.
Right now, you're able to download the full raster. So if I hit this button here, it will go ahead. I don't know that you can see it, but it'll actually download the GeoTIFF. So it'll download the underlying data set. You can also do the same thing with the convergence of evidence, compute the composite, and then go ahead and download that GeoTIFF as well. I haven't implemented like a state level clipping or like a clip of the based on like where the viewport is. That's a good idea. You can totally, I would invite whoever suggested that to put that in the feedback button. I think that would be a great feature. The truth is that these data are relatively lightweight. So even at a national scale, these data are not super heavy, but I think I can imagine that could be a really useful thing for disseminating this information at a local scale. So I'm happy to implement that.
Great, thank you. The next question is the model available for Puerto Rico and Hawaii?
That's a great question. Right now, these data, a lot of the backbone of these data are really driven by GridMet. GridMet is a CONUS, a contiguous United States product. So currently it is not available for Puerto Rico or Hawaii. That said, we are in discussions with NOAA, with NIDIS and with others about what the most appropriate underlying data sets may be. And I think that there's a really good argument for potentially augmenting the data or including different data for regions like Puerto Rico and Hawaii to extend this analysis. So I would, again, really appreciate if you were to put that in as like a feature request into the reporting toolkit right here on the feedback tab. That's a great way for me to kind of keep track of those. But that's a great suggestion. Currently just contiguous US.
Great, thank you. Next question, is there a GIS overlay or app available to show the Rossby or the jet stream wave?
Oh, that's a good idea. No, we have talked about bringing in things like, satellite imagery from GOES or other satellite imagery that would allow you to kind of see those atmospheric kind of trajectories. That's a great idea. And another place that I would welcome kind of a feature request in that feedback form, so that I can keep track of that. But I think that would be a really cool one to kind of think about, even early warning of where precipitation might be occurring, and try to kind of see how current atmospheric circulation patterns might impact conditions. I think that's a great idea.
Great, and the questions keep rolling in, so we'll keep going. I am a municipal water manager and am interested in leading indicators of potential drought. Which data sets would you consider most valuable as leading indicators?
That's a great question as well. And I think it depends quite a bit on your system. However, that being said, a lot of the time there's a great graphic that conceptualizes this. Is from like McNabb, I think from 1988, and it was out of the Illinois State Water Office. It's been used time and time again as a graphic to understand this cascading impact of drought through the hydrological system. And, the conventional wisdom is that generally you have meteorological impacts that are like observed first, and then you'll have shallow soil moisture and mid-depth soil moisture that then respond with response to that meteorological kind of forcing, which then propagates deeper into what we call the critical zone in hydrological science, or deeper into the subsurface that might impact things like streamflow and groundwater. And so, what you might look at is shallow soil moisture. We think about, this is the 0 to 10 centimeter soil moisture. I use this as a leading indicator of conditions. Like, for example, we had pretty strong soil moisture response from our precipitation event that just occurred in Montana, but things are drying out really quickly now. And so while shallow soil moisture can show that rapid impact of a precipitation event, then as you go deeper into the system, those kind of impacts might accumulate and show kind of longer term impacts. So I guess to get directly to your question, I would say using atmospheric meteorological data as an early warning, like, precipitation and evapotranspiration, SPEI at short timescales can be a good one to understand really recent conditions and might help you to understand how they might propagate through. But for a water manager, it might make more sense to just look directly at surface water conditions, for example, stream flow dynamics, to really understand surface water dynamics, which might be useful for your operation. So, I won't belabor this point, but I think the metrics that you choose as early indicators are really sector specific and depend on your kind of decision framework. But, typically shallow soil moisture leads other hydrological impacts. So I would recommend using atmospheric conditions and shallow soil moisture as a leading indicator.
Great, thanks. Now we have a couple questions on the architecture behind the dashboard. First, it is impressively fast, wow, of the cog/range request approach, client-side rendering and analysis, and Fargate/S3 backend. Which choices contribute most to its snappiness?
That's a great question, and the exact question I love to answer. This, I was, yeah, the first, the first dashboard we created was so slow, and where we've gotten now has been mind blowing. And I'll tell you the things that I've learned that are, I think, the most important is that um, understanding what precision you need for the data for visualization is the first key. So converting everything into signed integers that are basically super lightweight is the first thing, so that your IO and data delivery is just really fast. The second thing is there's some really great modern web mapping systems out there and libraries like OpenMap, that is OpenLayers, excuse me, that's really fast and does range requests really well. We're also using cloud optimized geotiffs. And so making those underlying data sets super lightweight is key. And then using some of these modern mapping libraries makes things really fast. And it's also a kind of a shift away from using kind of more traditional like web mapping services where you're actually hosting PNGs that have colors baked into the data. This is just the data itself. And so then we use, Chroma and other types of libraries to do the rendering of colors really quickly. And that allows you to get kind of more of a GIS feel to the data where you can zoom in, right, and on-demand change color scaling, and that is really only possible by actually rendering the data as an array. And then the last thing that I'll say is that a lot of these modern libraries are leveraging the GPUs in machines. So with the browser being kind of the architect of it, it's really leveraging the hardware in a different way. Instead of just using the CPUs in your computer, we're actually using the GPUs. And so it's a mix. And to be honest, like, it's magic. It's amazing how these libraries have developed and how web delivery has just changed. So certainly invite you to look at especially the front end code, which is right here. You can go to the front end dashboard code and see kind of in these different files that you can really see how everything is done down to the HTML itself. So I invite you to take a look.
Great. And David, I might actually connect you and Zach to follow up on a couple of the other architecture questions. Cognizant of time, there's a few more that I would love to get to. Let's see. Why was the 1991 to 2020 selected as the climate normal reference period in D3 when research indicates the change is already happening and impacting temperature and weather, particularly in the last half of that period?
Yeah, it's a good question. So actually, the default reference period from D3 is the 30-year rolling 30 years. So the 1997 to 2026. So we strive to produce data with the most contemporary reference period possible as the default, with the idea that reflects current day contemporary risk the best, because these probability distributions are shifting so rapidly. Using that most recent period is what we think is the most accurate representation of current climate, with the idea that we're always a little bit latent to the true distribution, as one of my colleagues once eloquently said. And so that argument is outlined really well in the National Academies report, which I think is a great resource here. But that being said, if you chose the 1991 or the 2020 normal as your reference period, if you do a share button, it will preserve what you choose as your reference period. So there could be arguments for using long periods of record in, for example, long-lived ecosystems where adaptation is untenable for, these old growth forests or something, and you want to take more of an ecosystem perspective to drought. But if we're talking about agriculture and societal decision making and water management, we think that using this rolling 30-year period of reference is appropriate, and we give some explanations for that here, along with some resources.
Great. I know we're getting close to the top of the hour. Zach, do you have a couple more minutes for those who can
Yeah,
stay on? Great.
absolutely.
Okay, let's see what's next. Great presentation regarding in situ soil moisture networks beside the Montana Mesonet. Could you use the D3 dashboard to incorporate many or all of the soil moisture networks and Mesonet networks within the National Coordinated Soil Moisture Monitoring Network, state Mesonets, USCRN, SCAN, SNOTEL, etc.?
Beautiful question, and I was just this weekend I've almost finished it. So I've got a new station data that you can't see currently; it's actually hidden. But I have a national soil moisture anomaly data set, point data set, that'll be up in the next few days. And that'll be for USCRN, SCAN, and SNOTEL, like you said. And then I'm also building a pipeline that's based off of Synoptic's data delivery system that'll allow us to access different mesonets. But what's key, and what, again, key to making these data sets available and making sure they're being used and making sure their attribution is being well represented, is getting permission from the local mesonet operators to make sure we understand exactly how they want their data displayed, exactly how they want their data attributed. With federal networks, it's a little bit more straightforward, but when we're starting to talk about state level networks, so we are building a system to do the national data sets that will be up soon, with proper attribution and all the methods, documentation, et cetera. And then we're in the process of working with different mesonets across the country, starting really with our NSF project, the NGP Rider in the Northern Great Plains, to really start to think about how attribution should look. How do we start integrating these different data sets, and how do we create these kind of harmonized products that leverage as much of the point data sets as possible, but do that in a really cognizant way, so that, again, we're making sure we're doing justice to the attribution of those data sets.
Great. We have a couple questions on past data. Is it possible to display past data such as SPI or precipitation during something like the 2011 drought?
Yes, this is a great question. And the answer is not yet, but soon. We are working on generating basically a historical archive of all of these data. We have a current archive. So if you go to resources, I'm assuming you can see this, and you go to data archive, you can see how the dashboard's been running operationally for the last several months, and you can access all of the data, say, from May 9th, and go through and see all that. And the idea is that before we have a slider, maybe I'll just do the slider to go back in time for the data that we currently have available, which is since its operational beginnings, essentially. But the idea is, yes, to have a slider that allows you to go back in time, and that record will go back, as far as we can with the methods that we are employing, that, would go back to definitely the early 2000s, to be able to kind of look at, current conditions with respect to historical past. So yes, that is coming. And again, if you want that feature, I invite you to add it to the feedback button once again, because that helps me prioritize kind of like where the demand is for different features.
Great. We'll do one more question, and then there's a couple more technical questions that I'll connect Zach to with the person asking.
Great.
The question is about the D3 getting confused with the D3 drought category. And I just wondered if you could say a few words about, how this relates or doesn't relate to the U.S. Drought Monitor.
Yeah. So I like to think, the U.S. Drought Monitor has created an incredible product that we're all, like, the drought science community is building off of. And And, in recognition of that, they have created a system that is internationally known. And as part of that is the, D3 is like a drought category, right? We think of D3 as being extreme drought for here, right? And so it was a play on words that is meant to kind of implicitly invoke the idea of drought assessment. It's not meant to, try to overshadow the USDM or anything like that. It's meant to just be a play on words that is something that people recognize what it means right off the bat. If you're in the drought kind of sciences community, I think it orients you towards the idea. It also orients you towards this notion of assessment and monitoring, as opposed to, more retrospective analysis or looking at paleoclimates or something like that. It's more about contemporary assessment. So, the USDM is, we think of them as a partner in the development of this dashboard. They've been very supportive of the development of this dashboard so far, provided really useful feedback. So the intent is not to confuse with the USDM or overshadow the USDM or anything like that. It's simply just a play on words. So I hope that answers your question.
Great. Thank you so much, Zach, for this demonstration, and to all of you who've attended and who've asked questions. I will follow up with a couple of you that we didn't get to, but I want to respect everyone's time, including Zach's, and just say thank you so much. We're very excited about the capabilities of this dashboard and its use in drought assessment in the Northern Great Plains and across the United States. So thank you, everyone, and enjoy the rest of your Wednesday.
Thank you very much.